Are you ready? All right. So thank you all for attending today. So we're going to hear mostly from Johnny, but I'll get us kicked off today. So how many of you know who Nordic is? Like, why are we even? Okay, so most of the room knows who Nordic is and what we do, all that good stuff. So I'm going to blast through the first part of this. And just want to make sure everybody in the room knows why we even have credibility to be up here talking to you guys about Zephyr and all that good stuff, right? So go ahead. Why don't we start plowing through the slides, and we'll get to the meat of this as we go through here. So there.
Intro yourself.
Is that me? Oh, it is me. So this is me, Scott Odell. That's my picture. So I've been in the wireless embedded space for 25 years, supporting customers in the Pacific Northwest. So I joined Nordic about 4 years ago. If you can't beat them, join them, right? So that's me.
And then, hello. So that's me. I'm sure you all know what I look like, so I'll replace it with my GitHub picture because... Yeah, is that a little better? Because a lot of the code that I put out for free are these unofficial samples that turn out in lots of different places, and they don't really know who Johnny Nguyen is, but they totally know who the toucan is, right? So, and some of the things, I'm the field application engineer for the Pacific Northwest, but I've also done a lot of product development before joining Nordic, and I joined Nordic because I liked Nordic development a lot, so I wanted to join them. Some of the stuff I've worked on, if you've totally seen these, there's very few companies that deploy these in the States and in Canada, and I worked for one of them, so I worked in a lot of that radio firmware. I've also done a lot of the FLIR stuff, if you guys have seen those cameras that do bicycle recognition and cars and all that stuff. As well as the cool little screen demo you guys saw at the table today, and I've also done a lot of open source. I wrote my own RTOS and open sourced it along with a gaming handheld for anybody who wanted to make a wireless gaming device. So that's who I am and the kind of stuff that I do. And then here's the agenda for today. So we're going to go through a Nordic intro really, really fast since everybody apparently knows about Nordic, and we'll talk about our products. Then we're going to briefly speak about Zephyr, and I'm going to show you guys some interesting case studies, especially around both demystifying some parts of Zephyr as well as clearing up some misconceptions around Zephyr that a lot of people have, especially coming more from the bare metal side of the free RTOS side into Zephyr, which is a little bit of a jump, and kind of clearing a lot of that stuff up, and some really unique case studies that went into contemporary products, right? But was like a useful way or workaround. So Nordic intro, that's back to Odell.
All right. So as many of you guys go ahead and flip through slides as I go through here. So yeah. So most of you guys already know Nordic. So low power wireless devices, low latency, and low bandwidth, right? We're not your 8K streaming over cellular guy, right? We are your local area network, your Bluetooth, your Wi-Fi, cellular, and then our cellular device actually in the next couple of months will be showing off that we can communicate directly to satellite. So some fun adventures there. Keep going on the slides. Again, ultra low power wireless products. One of the things about Nordic, right, is we developed everything in-house. So all of our silicons from the ground up, Nordic. We didn't do it by acquisition. So all the tools work really nicely with each product. And so it's all unified under a single one. So 54 series is the newest Bluetooth chip out. It's on 22 nanometer. Most important thing, active power number on that is about 1/10 of the 52. So continue to squeeze the blood out of turn up on those batteries. We're still the leader in BLE. We have about 40% market share. Our nearest competitor rarely even gets over 10%. So super strong in the BLE world. Yeah, keep going. These guys know us. Again, supporting all sorts of different protocols, everything from Matter down to BLE to Wi-Fi and just a bunch of the different ecosystems. And then all the support side. So 54, the silicon's done on the 54H. We still have some work to do on the development kit on that because on the SDK. Because it's just a complicated device. It's a 5-core device, 320 megahertz processors in there, 1 core for the application core, one core for the radio, 1 core for the security, 2 more RISC-V cores in there, a ton of memory. So It's a heck of a chip, but if you're doing something that's got a lot of algorithms running all the time, wearable, medical type applications, this part's going to be a sweet spot for that. Okay. Oops. 54L is out now. Dev kits are available, all that good stuff. We're hitting the market with it. We've got customers that are actually deployed in production on 54L now. And so this is really the 52 replacement, right? Unless you have a design going on today with that you need USB, there's no reason to go backwards to 52, unless you already had like your hardware done and you're just copy pasting. 54L, again, from an active power consumption, it's 1/10 the previous generation. So it's really crushing it in that world. We upped the ADC a little bit on it, a little bit more memory configuration. At the end of this year, we'll have 54L with USB on it, a little bit more NVM and RAM on it. So 2 meg of NVM and a half a meg of RAM. Then Wi-Fi, don't forget about us for Wi-Fi. So we are extremely low power compared to the nearest competitor. Again, we are not your 8K streaming guy, but it's your low data rate, Wi-Fi applications, windows, door locks, your thermostat, stuff like that you just home connectivity type applications. And yeah, super low power, non-China country of origin. Some customers need a little better supply chain story. And then won't be long before we put the peanut butter and the chocolate together with the Bluetooth and the Wi-Fi all on a holistic piece of silicon. So be watching the press releases over the next 3 to 4 months. Yeah. 91 cellular, lowest power cellular device. Our nearest competitor, we're a third lower power than them. So LTM, NB-IoT, again, low data rate, low power applications. We built a whole cloud suite to sit on top of that, so you can do all your location services, including Wi-Fi locationing, single cell, multi-cell, bring in the ephemeris data from the GPS, and get your specific location for your device. And you can do that cloud to cloud if you already have your own cloud device. So make it super easy to integrate everything. One of the things I should point out on 91 that we just do different from the competition, everything's is in a holistic system and package. Excuse me. Shouldn't have had a granola bar before coming in. So did you get that on camera? We have the application MCU in there, as well as the modem and the RF front end and all the passives and power management. So it's really easy to get it through and product certification, both the carrier and FCC and things like that. So try to make that process really, really simple for the customers. Yeah, go ahead. And then NTN, I mentioned that earlier. We'll be able, that same NRF51, 9151 device, we'll be able to connect directly to satellite, and we'll have those dev kits available probably at the end of Q3. So more stuff coming on that, super exciting. And yeah, biggest thing I think most of you guys know Nordic for is, we're here to support you. We actually like talking to our customers. So, if you need anything, DevZone is great. That's not where we staff our interns. Those guys usually have tenured employees of Nordic, and they have direct access to our silicon designers and our R&D teams. We got Johnny here as well. So there's lots of different avenues to connect with us and make sure, like, we don't make money until you guys actually get your products out in the marketplace. So why would we put barriers to that, right? So we want to help. We don't care what level you're at. We want to get you started and up and running and having fun with our products. Also, we have PMIX. Come by the table, check those out. And then again, the biggest thing is, Bluetooth, Wi-Fi, cellular, direct-to-satellite communication. It's all under the same SDK and under Zephyr, and it's really easy to migrate between different products and things like that. So with that, I'm going to turn it over to Johnny to get to the meat of things on why Zephyr is so cool. And I think you guys have probably seen some basic stuff on why Zephyr, and we're going to go into a couple more specific use cases that really highlight why it's such a powerful tool. And by the way, we've been doing it for like 8 years now, and we're really excited about some competitors coming on board and finally embracing Zephyr. I think it's great for the community, but yeah, we've been doing this for a while.
Howdy. So quick show of hands, how many people have worked with our chips and Zephyr before? All right. How many people have worked with our chips but pre-Zephyr, like the bare metal days? Okay, cool. So we're all in on Zephyr on our latest SDK, right? So all the new QD IDs that you've been seeing, all the new Bluetooth features, they've been with Zephyr. There's a lot of power that Zephyr provides for you in the form of middlewares and organizing your actual product and to make it more flexible, right? So, you know, if you wind up designing something on the 52 and say, I need like 500K more of NVM, I don't really change my application code. I just move over to the 54. I change my build system, right? But my code is the same. And that's one of the greatest things. And I mean, maybe a little bit difficult to say sometimes as like a Nordican, but before I joined Nordic, it was my favorite part is if I wanted to do something on an ST and I'm like, oh, I need ST for this one specific peripheral, but I don't want to port my code over. I don't really have to, right? And that was kind of my introduction into Zephyr was during the great part shortage of the pandemic. I had to, thank you so much. Hello, mic check, is that better? Yes. So sorry. So during the great part shortage, you know, before I joined Nordic, this was a couple of years ago, and my manager's like, hey, we can't get parts. We can get, and if we can get parts, it's not the same family. It's either the @SAM series or it'll be a different one, right? And I said, oh, dude, we got to port this code because we got to keep things moving, right? Production has to flow. The beast needs its food. So I said, you know, like, I actually ported this to Zephyr a year ago. Let's just hop SKUs. And I sandbagged a little bit, and I told him it took a week or a month per port, but it really took a couple days per port. And I looked like this awesome savior. I made 7 versions of the same product with the same code with different chips. And I was like, oh, it's just Zephyr, man. And they're like, great. We're still not touching it, but we're glad you're the Zephyr guy. So that was really cool and one of the awesome parts of Zephyr. And a lot of times people start to wonder, like, oh, like, what does the market look like, right? Like, where am I seeing Zephyr? I hear people talk about it, but is it going to be useful for me in contemporary devices and stuff like that? So something that you can do when you work in Bluetooth is, how many here have certified a Bluetooth device before with a SIG? Okay, so for those of you who haven't, one of the things, it used to be called a QDID, now it's called a DN, design number. So when you want to use the Bluetooth, like release a Bluetooth product, you need to qualify your device. We do a lot of that work for you. We qualify our stack. You reuse the number. You can actually, as a Bluetooth member, search that design number for the QDID you're interested in, any of ours, and you'll see how many, and it pulls up the FCC report and everything sometimes, right? You'll see how many contemporary devices are actually running Zephyr all over the world. So the momentum is actually quite large, and that's one of the really nice things about working at Nordic is you can see that information. So Zephyr's gained a lot of momentum from the form of project members, right? It's not just, obviously Nordic has been contributing to it and we push Zephyr a lot, but there's a lot of other honorable mentions like Intel, Google, Meta, and even a Volkswagen group is now a Zephyr project member. And if you guys ever do my equivalent of doom scrolling is going through PRs on GitHub, right, and reading some spicy comments. And if you go through the Zephyr one of my favorite ones I've ever seen is like one of our guys was arguing with someone from Intel. Like, no, the flash sync shouldn't be done this way because of this edge case. And it's just, you start to see a lot of internal buy-in, and that's a lot of fun, and Zephyr has been expanding. And it's for that portability, right? Like, it's a lot harder to convince somebody to change chips if you're going to go through this whole inertia of a code port. But Zephyr makes it super free, right? And obviously, I'm just showing more Zephyr. There's a lot of project members, so those animations are shown. The list has grown since last year. So that was the original list. This was taken earlier today. I was happy to see Honda there. I'm a big Honda guy. I have the same Civic I had in college. I love that thing. But yeah. So why Zephyr RTOS? Why did we choose it, right? And there was a lot of friction with us saying, hey, you are going to use Zephyr as the RTOS for our new code development, right? First of all we were focused on lower power. Nordic has always been kind of championing the low power wireless scene. Zephyr RTOS was the easiest way to do it. At the time, free RTOS was a little bit tricky with the tickless mode, and Zephyr offered a lot of benefits there. The other thing is, from a supplier side, since we support a lot of people and a lot of really small customers, like if you've ever reached out on the dev zone someone from Nordic replies. You could have been a student. You could have been maybe a startup. We respond to everybody. We want to help everybody. We had to pick the RTOS that had the most flexibility across ecosystems and the most code portability, right? So Zephyr offered a lot of that, but by offering all of that, it came with a lot of complexity. There's a lot of abstraction. That's everybody's friction. I hope to demystify a little bit of that today in my case studies, but that was the main driver for us picking Zephyr was code portability. We wanted you to write something once and focus on that. We didn't want you guys figuring out how to get the specific part of the radio working or how to get this GPIO. That's not where the bread and butter is. The bread and butter is what made your design unique, right? Like a mux is a mux is a mux is a mux. Nobody cares how you got it working. They care what you did with it, right? And so we kind of wanted to embrace that. So one of the weird things about Zephyr in its hardware abstraction is the build system. Just quick show of hands, how many people here are registered for the workshop? Okay, so how many of you completed the installation for the workshop? Okay, and of those, how many of you actually clicked the build button? Okay, for those of you who haven't clicked the build button, the people who clicked the build button would have seen a million things pop out in the console. It did a whole bunch of stuff. So I'm gonna give you the quick 1,000-foot view of what it did. It took our SDK, and it took your code, and it used West, and did all of this black magic brujeria, right? And then it created some kind of application, right? It pulled in things from the kernel, everything you configured not to put in, like, I'm using Bluetooth, but I'm not using GPIO. It didn't pull in those drivers, right? Because the RTOS is massive. You don't need everything. So the kernel gets configured at build time. And it's like, do you need I2C? Nah, okay. I'm not going to take any of the I2C drivers. And then it uses kconfig and a project config to kind of decide, like, all right, this is how I've configured my project. These are all the modules I'm going to include. And then it has to describe the hardware, right? So that is the whole device tree thing, hardware abstraction. Your GPIO code to like toggle an LED is the same on all of the devices, right? I could give you a Nucleo and a Gecko and a Nordic kit and a Feather. I could give you our dongle, and the Blinky will be exactly the same. It was amazing. And this is one of the key pieces was that hardware abstraction. So we've now used device tree files to describe the hardware. Everything is a device. Your GPIO, your LED, your flash, your CPU, everything is a device now. And it went through this whole thing to spit out a binary at the end, and the only thing you really cared about is your code, right? And that's very cool in Arduino-y. Also, how many people are Arduino fans? So how many of you knew that Zephyr is now like the official RTOS of Arduino? Yeah, yeah. So that's pretty cool developments on that front. So the other cool thing that we added is how many of you have used ST before? Yeah, so one of the cool things about that, and I as a Nordican, we did it in a different way, but it's still cool. We really like the GUI. We like being able to see the chip and click pins and say, I want this to be an LED, and device tree is awesome, but it's code and it's a different syntax and there's always friction there, right? So we made a GUI that lets you click pins on the device and it generates device tree code as you configure it with drop-down menus. And there's a little toggle in the top right, and we can explore it in the workshop and stuff, but it's a pretty cool symbol. It's a little chip symbol, and it'll flip-flop between device tree and the GUI. So it'll flip-flop between the code and the GUI. So all the device tree is, it's a hardware description language, but not really HDL, of like all the peripherals on your device, right? Which is really confusing because in the power management stuff, I'll get to that because there's power management and device power management, but device power management is not the system power management. It's for a device. It's just from the naming enclosure and convention. So the other reason we picked Zephyr is because we focus on the wireless stack, and we also help with a lot of the software, and we contribute to it, and everybody does, and that's awesome. All you guys really have to focus on is this very top layer, right? That's like the new landscape. Our Bluetooth just works, Zephyr just works, and you focus on what makes your thing special, right? So we're going to go over some really quick misconceptions. I have proven and measured these misconceptions myself, and you'll hear it a lot, and I hear it a lot when I talk to people. People say Zephyr is not power efficient. It absolutely is. So this is a Bluetooth connectable device what you make out of that, it could be whatever you want. I could put this in a tire to measure air pressure. I could throw this in my kitchen and have it tell me the time and the temperature and humidity. I could do what it's a blue. We all know the wonders of Bluetooth and connectable stuff. But, you know, if it's not plugged in, I've got a battery. Sometimes it's not a very big battery. Maybe I want a coin cell AA, tiny lithium battery. This Bluetooth connectable device on the 54 series, which is all magical and high power, has 9.4 microamps of charge over a 10-second interval, right? So this wasn't like a snapshot of, because when you read the data sheet, you see peak currents of the radio, and it's like, oh, that's milliamps, that's really high. And then it's like, oh, but when I'm sleeping, I do this. I barely thought about those things when I wrote this application. I said, give me a 10-second window. I want to know the average, because I want to know how many days do I have on this coin cell battery. And if it's hundreds, awesome. And there's some cases where people will say they mathed out their battery to last like 3 months, and they came back 200 days later, and it's still alive, right? The only thing I did differently, and this was one of the powers of the device tree. So now we have this concept of device. I'm collecting sensor data over an I2C bus. That's not really power efficient sometimes because I use a high frequency clock, right? Like everybody knows, high frequency clock, hundreds of microamps. But I say, okay, well, let me power down how many of you have ever powered down a peripheral on a chip before when you're not using it? And you go through the register and you go through the data sheet and you step through everything, right? And you're like, okay, finally, I saved my 100 microamps. It's amazing. I used 2 lines of code in Zephyr, 2. Nordic handled the implementation of the power management in the driver. The user, in reality, only writes 2 code. You call Zephyr's device power management. You say, suspend this device, right? Because you have this concept of the I2C thing being a device. You just ask it to suspend it. It goes through our code and does all that, and you only wrote 1 line. And it was pretty funny. Before I joined Nordic, they were trying to get the power numbers down, and they thought I was an absolute genius because I got the power numbers down super low in like 3 days. On the they gave it like high priority on Jira. They was like, we got to get this thing like down to this. I said, it's done. They allocated 3 months, and I was like, no, dude, guys, it's a week. It's like 2 lines in Zephyr. We're good. So to clear the misconception, Zephyr is not power efficient. It totally is. When it's consuming too much power, it's something else on the board, or you're just not playing with it correctly, right? Misconception 2, it's not memory efficient. It totally is. You can never compare an RTOS to writing, like 4 assembly instructions to toggle a pin, right? You've got an R jump and then just a load and a load, right? That's pretty much all you got to do to toggle a pin. And if you want to toggle a pin with a delay, that's only a dozen more instructions. An RTOS is never going to beat that. But how many things are only blinking an LED in reality, right? There's a lot more that goes into it. So here we took just blinking an LED, right? And yeah, you're using the old bare metal SDK. 2 kilobytes of flash, 4 kilobytes of RAM. With our RTOS, so the NRF SDK row is for the RTOS, you've got 5 times the usage on the flash and a little bit less on the RAM. And you're going to say, oh my God, the RTOS is not memory efficient. But let's use a little bit more of a realistic use case. Let's make a Bluetooth application. Like we see them all over the place. Let's just take a peripheral that we can connect somewhere. So the NRF5 SDK was our bare metal SDK. So we took and made a prototype with the NRF5 SDK, and we looked at the bare metal flash usage and RAM usage. So we used 110K of flash, 8.5K of RAM. Okay, still, it's kind of big, but like it's okay. That's workable. There's a lot of chips that'll fit on. Then we bring in the RTOS and all the memory optimizations you can make in the RTOS. Without optimizations, I actually used less flash. I used more RAM, and RAM is expensive, but I feel nowadays it's not as expensive as it used to be. We're not working with bytes anymore, right? We have kilobytes to work with. Our 54L has 256K. There's a lot of wiggle room. And an RTOS is always going to use more RAM because you have thread stacks, and then you have to have the scheduler, and you have all this IPC, and especially with Zephyr, you have the kernel services and all that. So it's going to use more RAM, but it's actually more flash efficient, which is awesome because everything that's Bluetooth, what do we want you to do? We don't want people plugging stuff in sometimes to update it, right? We want to connect over our phone and do a firmware update. We want to do it remotely. Maybe there's not even a port to plug in, right? Sometimes it's closed off and I need to update it remotely. The antenna is the only thing I can talk to. Well, what does that mean for flash? I've divided my flash space in half, right? I need a backup image if the firmware update fails because it's over an RF link. If it fails, I want to boot back to what I had originally. So the fact that the RTOS is more flash efficient is actually more helpful to you than it being less RAM efficient. And that's without optimizations. You can always optimize in Zephyr. It's just a lot different from what you're used to in bare metal applications. So for example, let's say I'm debugging something and I added a ton of logging everywhere, right? I've got logging in every single thread and in my driver inits, and I want to know what's happening where without attaching to the debugger to halt it. I don't want to interrupt the wireless stack. I just want to see my logs. Well, that uses a lot of space. There's a thread that actually processes all your calls to log or printf or whatever you're using, right? Well, maybe I can just disable all that. Oh, dude, now I have to add this if guard with a global defined somewhere to protect all the logging to disable it, like the way you've always done it in bare metal. The convenient thing in Zephyr is you just disable the logger module with one line. You say, I don't want it. And it'll say, okay, I'm not going to build logging. I'm going to ignore every single call you had, all these thousands of lines of logging, because I want to know how much space I'm actually taking without logging. So in a lot of our projects, you'll see these. So if you remember earlier, I mentioned the project config, right, where you configure the kernel. And in our projects, you'll see things called project.config and project minimal and project release. And maybe there's 7 lines in the basic project config, and we want a lot of stuff defaulted on. But in reality, you don't leave a lot of stuff on, right? You get this thing as cheap as possible so you can make a bunch of it and get as much margin as you can. So we give you examples on what it looks like to optimize all these settings, right? I could say disable these certain services, reduce the stack size of this, be really efficient here. Maybe use this deferred logging mode somewhere else. So we have multiple configurations of it. And instead of managing the source code, I'm not managing that between a debug and a release anymore. And I literally just have one file that configures for debug, configures for release, configures for different types of boards even. So hopefully that clears the misconception that Zephyr's not memory efficient. It totally is, just not in the really weird edge use cases, but in most contemporary applications, it totally is. Misconception 3. I put misconception because I didn't want to change the title card, but this isn't a super misconception. People say it's overcomplicated. Zephyr is super complicated. There's no sugarcoating that. It's way more complex than anything that you typically work with in this space. Like, instead of just having a thread and a basic scheduler, like, oh, well, what's the difference between cooperative threads and non-cooperative threads? And how do I toggle the I/O without device tree? And right, like, there's suddenly a lot more meat to it. However, I put it depends because it depends on what you're making. If you are making something really complicated, it actually cleans up the code a lot with all of the process services and the multi-core aspect of it, right? How many of you have ever worked on a multi-core device in bare metal or assembly? Was it fun? It was fun. It was fun from an edification perspective, and it wasn't fun when you had to go to sprint reviews or something and explain why it's taking long, other than it's really hard. So one of the things you saw on the 54 was that we have a little RISC coprocessor, right? And then as soon as I say, oh yeah, it's multi-core, you get this uneasy feeling. I see it all the time. Say, yeah, there's multiple cores. It's like, oh, whoa, hold on. I remember the last time I ran into that. What does that look like in the Zephyr RTOS? So remember earlier on, I showed you that build system where you point at your hardware, right? Well, it's already set up to point at different hardware in the build system. So all you really have to do is the same process of making a Blinky. I make a project, and instead I just point it at the different processor. It's on its own. And then I can add IPC however I want. The build system takes care of it. As the world goes more and more multi-core, the devices go to smaller and smaller process nodes. Extra processors get peppered in. I mean, why not, right?
I'm going to just add to that real quick. Like, going to 22 nanometer on the 54L, the device, the chip itself became so small, we actually had to add more die area in just to get all the I/O out, right? So it's not about like trying to get the die as small as possible anymore. It doesn't exist. So we're going
Yes. This is a fun one, and I'm going to show you in one of the case studies. You can totally still use assembly and register level stuff in Zephyr. There's nothing stopping you from doing that. A lot of people think, oh, everything is robbed from me and I have to deal with this abstract. That is not true. I have personally implemented decade-old assembly libraries that we ported to new architecture and had it in a Zephyr application. I said, totally. If you wrote it reasonably and you protect your registers, right? For those of you who have worked in assembly, you protect your registers in a smart way and the architecture matches. There's nothing stopping you from using assembly in Zephyr or even doing anything register level. That's all. At the end of the day, it's a microcontroller. It's not suddenly all magical and mystified because you're using Zephyr. So it's more feature rich than its comparisons, but the feature richness is what gives you a lot of power as a developer, right? You start to look like a superstar to your managers. At least I did. Like, it totally saved my keister. I looked super smart all the time, and I'd never mentioned this was super simple because it was Zephyr, unless I was trying to convince them to move another project to Zephyr. I said, like, I'll keep saying, no, this shouldn't take a month, and every other chip, it'll take months, and then I'm done really, really fast. In case it's obvious that's why I went to Nordic. I said, no, I don't want to work on these other chips anymore. I just want to work on these. So now we're going to talk about a couple of interesting case studies. I'm not pointing at specific devices, but these were contemporary devices out in the wild and specific problems that we had to solve, right? So, execution quarter. This is one of the best things. So, how many of you have ever seen a Blinky? And it's pretty much like one main, and it does like one thing, and that's it. And in Zephyr, that's totally not the only thing that happens. We just don't want to show you yet, right? We don't want to scare you off. And one of the most common interview questions is always, who calls main? And that's a great question for microcontrollers. And don't ever ask somebody for Zephyr because most people won't answer it, except all of you are going to answer it today, because this is actually the Zephyr execution order. So at reset, there's an early boot sequence that happens, and you'll start to see lots of, anyone here know what grep is? What about like find all? So if you ever want to have a good time, just grep the Zephyr repository for the word sys init. And you'll start to see the different priorities that we initialize LEDs and we initialize clocks and all these other devices. And you're like, oh, well, that's interesting. So there's after the early boot sequence, there's a pre-kernel 1 and 2, and that's where you start to see all of those sysinits, right? And there's post-kernel and application. And all of these things execute well before your single line of Blinky. You just never really see it until it matters to you. And I'll give you an example of a case study. So I mentioned firmware updates earlier, right? So we all know how bootloaders are a thing. Not everyone has worked with bootloaders, but we know I totally have to load at boot and do a bunch of stuff. And Zephyr includes MCU boot. So it may seem extremely obvious between a bootloader and application that I want to toggle a pin in my bootloader and keep it high until my application says everything is all good. That's a pretty common use case, right? You have the little status slide in your device that's like, oh man, it's stuck in, hit reset or something. If you tried to do something like that in Zephyr and you did not touch that LED or that switch or that GPIO in your application, it would still turn off, even though you turned it on in your bootloader. Well, why is that happening? Because of the actual execution context, right? You did it in the bootloader, then the application called the driver initialization, which happened somewhere over here before your main in your application, and then that ran at a certain priority, and it totally put the pin back to the defaulted state. Oh, what do I do? How do I even solve that? What tools do I have? So Zephyr has this other really cool thing, and it's been one of my favorite tools. So really quick, how many of you like to manually initialize things? Right, you want to know when you're initializing it. And there's a lot of friction in Zephyr because as soon as you include it in the device tree, it's initialized, and it's a little bit undersold because that's not necessarily the case. There's something called deferred initialization. And it's basically a single line flag in the device tree where you say, oh, I want to initialize this later. Just pull in all the code. And then it functions exactly the way you're used to, where you manually initialize, and that solves this problem, right? The other way you could do it is you could use GPIO hogs, and it depends on the actual priority of the drivers. All of the drivers for the devices you pull in are in that special grep sys and it happening in different priorities. They're happening in different orders. So that's something to remember where it's like, oh, there's a shared pin between these devices, and I'm not getting any. Maybe on a Linux computer, you try to do something like that on an actual personal computer, and then you seg fault, and then you have anxiety, and then it goes back to boot, and then it seg faults again, and you're having a terrible time. Sometimes Zephyr lets you get away with it because the microcontroller land tends to be the Wild West with that stuff. There's no MPU sometimes, right? And it's like, oh, these two code blocks are sharing this hardware address. That's fine. Yeah, we trust you. I mean, you're programming in C. You know what you're doing. It's dangerously efficient. So it's important to keep this stuff in mind, right? Like these things happen in the background well before main happens, and that higher level thinking tends to not happen in a lot of bare metal contexts because you wrote it. And you didn't write any of it here, but it did get written and it does run. So that's an important thing to keep in mind, the execution order. Case study number 2, interprocessor communication and ownership, right? That's a mouthful. So interprocessor or interprocess communication. We'll start off with interprocessor. You guys remember I mentioned the device tree to describe hardware earlier. Well, what if it's a different core in the same chip? Maybe I want ownership of this GPIO in my second CPU and not my first one. It's like, oh, well, what do I do? Status equals reserved. So there's a status flag in device tree if you've ever seen it. All status does is either enable or disable, except now there's a reserved. What is reserved for? You're basically telling the build system, hey, I want this driver, I want this I/O, but this CPU is not using it. I want you to initialize it, I want you to set it up, but I want it to belong to a different CPU. And it's a one-liner, which is really awesome. You don't have to work with a claw, those of you who have ever done the Delfino multi-core development. And GPIO forwarding is another thing you could do, right? So one of our devices is multi-core between application and radio core. And maybe I want to do something with the GPIO on the radio core, but I want to control that in the application of my application core. You can forward the GPIO, and it's still just a device tree thing. You're not manually writing to specific memory ranges or anything like that. You're just using the device tree API, and everything is exactly the same, and it's super plug and play. I like plug and play. I'm a lazy engineer, right? Yeah. I like being, I'm like, dude, I'm super lazy. And then the other thing, I put inter-processor communication, but I kind of hate the IPC acronym because IPC can also mean inter-process application, or communication, not application, right? So I have 2 threads and I want to communicate between them. I have 2 threads and 3 different source files I want to communicate between. That's like one of the first things you do in an RTOS. Usually it's a message queue or a FIFO, but I added a little table here to show you that there's no one default way. Like when you go to FreeRTOS, they'll say, how do you want to do it? A, use message queue. Zephyr has ZBus, we have IPM, we have OpenAMP, we have IPC service, and we have our RP message service. We have a lot of different ways you can communicate between tasks. And for those of you who are going to the workshop, we are totally going to work with one of them. You're going to feel super smart and talk about threading. And I feel like if you've never done multi-threaded applications before, the moment you start talking about it, everyone really listens. They're like, this guy knows what he's saying. Logging. I mentioned logging earlier. How many of you have ever had to debug something with a lot of prints? Yeah, it's a very, very popular debugging. I like it a lot. I don't want to attach a debugger. They're really expensive sometimes, or my board is really small. Can we still hear me? All right, cool. So logging. Logging is this really cool utility in Zephyr. It's very, very useful. And there's lots of different backends. It's this giant software block that has one thread called the log processing thread. And all he does is you decide what the endpoint is, right? And you use the same function, which is log underscore some severity, and it's a printf. And you can make print k go that way too. It's pretty cool. It's pretty slick. And we've all worked on different hardware. And the reason I'm mentioning this is your logging will work on the same on all your hardware. I say, how is that possible? One of the things you use with the Zephyr folks are really smart about this. One of the things you'll use is you'll decide what the back end of your logging is. Because most of it has to stay the same, right? Like, all I'm doing is string stuff. It doesn't really have to change between chips. Why should it? What does change is the actual hardware it comes out of. Am I coming out of a UART? Am I coming out of a SPI bus? Am I coming out of some other method that I'm going to mention in a sec. So that's a one-liner. Zephyr did a really good job of, you say, I love the naming, logging backend. So you could say you're a full stack developer, right? And you use exactly the same code between devices, but you just change what the backend is. All of your logging is the same, and you can print it exactly the same way. This first little thing here is called deferred logging, and this is one of my favorite things on the planet. Because when I mentioned to you that there's another thread that actually spits all the logs out in Zephyr, your first concern will be like, well, what about my execution time? I'm now slowing it down with all of the serial stuff. Deferred logging is your friend, and it is an underutilized feature. What deferred logging does is it makes it so all your logging happens way later. It absolutely increases the memory space of the logging thread and decreases the priority and a bunch of other cool stuff. And it makes the code doesn't change at all, but it makes it so it is as lightweight as possible. It's a basic mem copy, and I'll grab it out of the queue later. And if this is fast enough for me doing proprietary radio stuff on 2.4 gigahertz, it's definitely fast enough for what you're doing. Unless anyone here is doing DDR5 stuff, then I'm sorry, you probably shouldn't use logging. But that's okay, we have tools for you. The other thing is RTT logging, and this is not a Zephyr-specific thing, but how many of you know about RTT logging? Right, do you love RTT logging? When it works, right. One of the logging, for those of you who don't know what RTT is, basically in RAM, you have this nice magical control block, and you can pull logs or serial data out of the SWD port, because you said, oh, I used every single pin on this thing except the programming header. Well, that's fine. Use RTT. And you just store it in memory. The code is exactly the same between a UART log, your other types of logging, and RTT logging. It's exactly the same. You just change the back end. Really cool on I/O constricted devices. But remember what I said about bootloaders and applications. A lot of pain points exist between RTT logging, between bootloaders and applications. Why would that be? I mentioned it really briefly, but is the show of hands, how many of you think that the RTT log is stored in non-volatile memory, the control blocks? Okay, how many of you think it's stored in RAM? Cool, awesome. Yes, it's stored in RAM, which is cool, and we got compilers that do all kinds of cool stuff and decide what goes where in the linker and blah, 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 blah. We've all done computers. Well, if I used RTT logging in my application and I used it in my bootloader, don't they totally have to be in the same place? Right? But I never touched where the control blocks are. And that's where the trickiness lies, right? Understanding that execution order, that context from boot to application to main. And there's tons of different ways you could decide the buffers are in the same place. But that's just an important pain point, and a lot of people have that pain point. The simple thing is to flip-flop which one is using logging, but if you make sure they're in the same memory location, you're all good. Clock sources. This is a pretty cool one. So the NRF54L15 can have a 4 megabaud UART. That's pretty fast. Bit errors be damned, that's pretty fast. But that's pretty non-standard, right? Most of the time you see it go up to 1 meg. So like, what are your standard speeds? Like 96, 11, 115.2, 256, and then a meg on the high end with flow control, right? 4 meg. The hell is 4 meg? How do I do that? Oh, well, I'm using Zephyr, and devicetree is totally awesome. All I have to do is change the baud rate, and it's going to go into the driver and do exactly what I want to. This is not true. The reason is it's reusing the same driver code, right? So everything's behaving exactly the same. And it's going to cap it out at 1 meg because almost everyone's UART is 1 meg. And you say, oh, you can't do this in Zephyr. How dare you make me use Zephyr? I've now been restricted. And this is why I always make the comment. It's just microcontrollers at the end of the day. Printed here is the, ooh, where'd it go? Okay, cool. Am I static? Hold on. Cool. So here's a really big picture, and it's an eye chart, and I'm going to tell you what it is. This is the baud rate register of the UART peripheral on the 54L. And down here it says baud rate 1 meg at this value. And there's only one little segment of text that matters here. 1 megabaud when UART has 16 megahertz peripheral clock frequency, right? If it's 1 megabaud when I have 16 megahertz, and I'm using a clock that's 8 times faster, can't I just say that I'm actually using 300K and get over 1 megabaud because it'll multiply by 8? And that's all you do. So it's kind of a weird case of hacking device tree, right? I'm just saying, well, I know what the clock sources are. The device tree doesn't know, but it's still, at the end of the day, putting a number in a register. So I'll just put what I expect the baud rate to be if I were to divide by 8, because then it'll feed to an 8 times faster clock. And then wham, bam, it works exactly as expected. The drivers, all the code is exactly the same. I just had to be smart about my clock sources. Manual drivers and assembly. So you heard me mention that with Zephyr, you have all of this automagical driver work done for you by all these really, really cool, smart people, and you feel really great. And then when it doesn't do what you want it to do, you get really mad at Zephyr. I know I did for about a year before I joined. There's nothing stopping you from using your own drivers, right? Absolutely nothing. It's a microcontroller at the end of the day, and Zephyr feels super big and complex, but you have absolute control over it. And this one line is pretty magical. It's called compatible. So really quick, who here has worked with device tree and knows what compatible is? All right. Compatible is in device tree, and it's a simple line, and you usually use it to say, I guess the really layman way I'll use it and the way I see other people use it is, these are the drivers I'm going to use. Awesome. Let's say I want to use a sensor from Bosch. In the compatible field for the driver, I'm going to say compatible equals I squared C, comma, the name of the device. And then Bosch, the excellent folks over there, wrote this whole driver, and I don't do anything. Let's say I want to use I squared C. All right, I want to use I squared C on a Nordic device. I say, oh, well, the Zephyr API code is the same, so how does the driver change? Compatible, right? So in a lot of the code you're going to see on Nordic devices, it'll say compatible equals something like NRFX, comma, something. So those of you who have worked in Nordic bare metal, you're all familiar with NRFX. You absolutely love NRFX. I love NRFX. NRFX and curl are like my 2 favorite things on the planet, right? So under the hood, it's all calling NRFX. You totally could just ignore the device driver and say, nah, like, I'll just disable it in device tree and initialize it myself with NRFX. Nothing stopping you from doing that. If you know what you're doing, the RTOS is meant to only be a tool to make your development better. It does not make sense that they would restrict you from actually using your own drivers. And the same way that we added our drivers into the SDK, Bosch added theirs, TI added theirs, everybody adds their own drivers. You can take that same structure in and make your own for whatever device you want. Maybe you'll actually see in the contributions if you go, anyone here like Adafruit? You like buying stuff off Adafruit? I love Adafruit. If you look up the product on Adafruit in the Zephyr repo, sometimes it's not even the person who like has the chip company on it, right? Like it's just some guy who really likes this Adafruit sensor and he put the driver into Zephyr. There's nothing stopping you from just grabbing it. You have a lot of control in Zephyr. People feel like it takes away control. The number one misconception I'd like for you to walk away with is Zephyr is powerful and it never robs you of control. You just have to kind of have this weird way of thinking about it. So I mentioned I love NRFX. How many of you have worked with PWM? Right on. PWM, usually you just mess with a duty cycle and it gives you this awesome waveform and you either make it bigger or smaller and it's nice and symmetrical and that's really cool. What if I want to do some really arbitrary sequence? What if I want to use PWM as a spy? And I want to send it packets. Oh, that's cool. Maybe there's some chips that do that, but not all of them, right? Cool. I want to use a Zephyr driver. That's not going to work because they had to least common denominator this API, right? It's got to work with everyone's PWM. So Nordic's PWM is really cool, and it lets you put arbitrary waveforms in RAM and play them however you want. So these are 4 distinct sequences that look like, actually, one of them is the standard for credit card payment system, because I was being funny. But you can load arbitrary sequences in RAM and play them over PWM. But I did not use Zephyr for it. I just created my own driver with NRFX, and I said, hey, I'm going to pass you an arbitrary waveform, and you're totally going to do that. One of these is like a spy flash. Like it's just random communication protocols over PWM. But you have power over the drivers. You would not have been able to do this with the Zephyr API, sure, because I mean, how many of you have heard of a PWM that does that? That's really weird. I thought it was really weird. Animations. So those of you who have worked with Nordic devices before, how many of you use PPI? That's about the response I'd expect. I will give you a quick 1,000-foot view on what PPI is. Let's say that I have one peripheral and I want it to talk to another peripheral. And I want some kind of action from that, but I don't want to use my CPU at all. Sounds pretty rad, right? That sounds more like an ASIC thing. Doesn't sound like a CPU thing. So Nordic actually put a peripheral called PPI, and it's going to be a mouthful, but it's Programmable Peripheral Interconnect. That's a lot of words, but it does exactly that. How many of you have ever used the chip with something like that before? Right. And they're all pretty different, and they're non-standard, so how can you make one unified API with it? Nope. So there's no PPI driver in Zephyr. But there's libraries, right? And the reason is because the PPI that works on this one is not the PPI that will work on an EFR, is not the PPI that will work on an ESP-C6. They have different names, different registers, different ways of working. That doesn't mean you can't do it. This is a Zephyr application doing everything as expected. I'm reusing callbacks. It's super cool. And all this does is it's a timer. Love timers. And when the timer expires, I want to collect a bunch of ADC samples. Pretty common use case. And then I only want to be interrupted by the peripheral when I have all the samples. I want all 100 of them. That sounds really rad because I hate collecting the samples and averaging them and all this stupid. It's not stupid. It's fun for some, but I don't want my CPU doing it. I have important things to do like Bluetooth and product stuff. So this is with PPI. The CPU only wakes up to collect the samples and print them. That's the only reason the CPU does anything. Everything else is done autonomously with the PPI driver, manually, and outside of Zephyr. It doesn't mean it's not I'm still using the, if you look, the INF, that's the logging output. Still using Zephyr, still using threads, but I use PPI here. All it says is you could change the actual power lines and see the ADC's reflections. All right. How many of you have programmed an assembly before? Right on. I hope not to give you PTSD with this image, but this is an example of I really need to do something in assembly. But you have this RTOS, and I don't know what happens, and I don't know how to do this. Well, like, you could totally do inline assembly. There's nothing stopping you from doing inline assembly, right? But inline assembly sucks if I've written a bunch of .s files, doesn't it? Because now I have to take every single line of assembly, and I have to put it into the inline quotation marks, and it's a disaster. That's not a smooth thing at all. And I don't think Zephyr can handle building .s files, can it? It totally can, because there's .s files everywhere. It's a microcontroller at the end of the day. Here's an example of it executing with the assembly instructions. So this is all still the RTOS, and it says just some inline assembly stuff to clear the register, add the register, and store it, right? And it gives you the same result as calling an external assembly function in C. So you could have, as long as the architecture matches, because that's what matters for the instruction set in assembly, you can include external assembly files all fine, and you'll get the same results. There's only one problem, and that's if I were to have called print K somewhere here without storing the result, what do you think would happen? Raise it. Anyone volunteer to think what would happen if I called log or print K without saving the result of the assembly function? Ideas? Exactly. You clobber it. And you say, oh, no, Zephyr can't. No. It's just doing all this other stuff and clobbering the register because I wrote it poorly, right? Time. This is the last case study. And this is for something really, really fast. So Nordic radios Bluetooth is really slow, but Nordic radios are really, really fast. There's nothing stopping me in Zephyr from creating an application where I tie sub 100 microsecond radio activity to GPIO at all. Still done through PPI. That's 8 kilohertz reporting rate over radios. Bluetooth is 7.5 millisecond latency, right? We can get to the sub 100 microsecond. And those were the cool case studies. And the only other thing I have to set up, some awesome open source mentions. If you guys like smartwatches, the guy at ZS Watch does an awesome job. It's open source software and hardware. Healthy Pi Move as well, and we have the thingies. And those of you who really like mice and keyboards and you like to copy paste a lot of work, we have a full application and hardware reference design that you could rip off the internet, and it's all Zephyr based. And you'll have a mouse. You could seem really cool and just focus on the actual productizing side of it, right? That's what makes it cool. Custom keycaps, special functions, right? And that's it.